Hi, I'm Akshay Baheti, and welcome to the Cafe Rongen Journal Watch, where we review certain important or interesting radiology articles. This time, we're going to discuss an article on artificial intelligence which was published in Lancet late last year on the use of AI in detecting critical findings in head CTs. Before we actually delve into the depths of the article, I'm going to discuss a little bit about AI in general, and people who are already aware of it might actually skip to the latter of the video. Um, but AI is essentially like an external interconnected set of neurons which pretty much mimic the normal human brain. The best example I can give of AI, which most of us must have encountered, is actually Facebook. So, for example, if I upload a photo of myself with two of my good friends on Facebook, Facebook immediately puts some suggestions for tagging these photos, and that's based on the faces that it sees, and they're usually accurate suggestions. How does Facebook do so? Well, by using AI. And as I said, AI is something which mimics the human brain. So, how do I, for example, recognize Tom Cruise? That is because the first time I see Tom Cruise, someone tells me that this is Tom Cruise, this is how Tom Cruise looks. And the next time I see the same person, I can identify him as Tom Cruise. And that is pretty much what we do in AI. We give AI tagged or labeled datas or data sets and teach it to learn that any similar appearing data in the future it should be labeled similarly. So, for example, if I tell an AI software that this is Donald Trump, so is this, and so are these, and then upload a seventh photo of Donald Trump, the AI software should be able to recognize that photo as one of Donald Trump. However, in reality, it is not so simple, and we need a lot more photos or a lot more data to train AI to become accurate. And what exactly do we do in radiology? Well, pretty much similar. So even in radiology, what we have to do is to take a large data set of as many images as possible, label the data accurately, and then run an AI software on it and let it learn from that data set. We'll go into details of this later, but essentially what most softwares or studies are now doing is trying to label data as normal or abnormal and let the AI software learn from it. But we can also do more than that. We can label something, for example, as a normal chest x-ray versus a chest x-ray which is abnormal and shows consolidation, or a chest x-ray which is abnormal and shows pneumothorax, and so on and so forth. But we can actually do much more than just that with AI. So for example, here is an image of a pretty homogeneous appearing small right adrenal adenoma. But as I zoom it further and further, I realize there's actually a lot of heterogeneity in this lesion, and each and every pixel is actually different. And the human eye cannot perceive these differences very well, but an AI software or a texture analysis software can certainly do so. And that is where another huge promise of AI lies. That based on this analysis of pixel level information, AI can possibly predict that a lesion is benign or malignant. It can probably predict whether this lesion will have good survival or poor survival, whether it will respond to chemotherapy or not, what are the mutations present in that lesion, etc., etc. And this field of radiogenomics is also a huge potential application of AI and machine learning. So how do we actually train the AI software? We start with a large data set. A huge chunk of the data set is the training data set, which is used to train the AI model or fit the AI model. A smaller chunk of this data set becomes the validation data set, which is used to evaluate the trained AI model and fine tune the parameters. And because ultimately both of these are part of the original large data set, what we actually need is a third external test data set, which is then used to provide an unbiased evaluation of the final model. The big question is how much data is actually enough to be accurate? And frankly, the answer is as much data as possible. The more the data, the more will be the accuracy of the AI software. So for example, after running 2 million miles in 2016, this headline says that the Google car now drives better than a 16-year-old boy or girl. And how many miles would you need to drive as good as a 16-year-old person? Well, maybe 100 miles, 500 miles, 1000 miles, 2000 miles. Certainly not more than that. So our equivalent of uh, 500 to 1000 miles is actually 2 million miles for an AI software. So certainly the AI software needs a lot of data. What is the current scenario in radiology? Of course, a lot of tremendous research is happening, but unfortunately, majority of this is on very small data sets, often just hundreds to thousands of images. And because of this paucity of numbers, some studies may actually avoid having the test dataset completely and just work on the training and the validation datasets, which is not the ideal case scenario. Also, most softwares attempt to just answer binary things, normal versus abnormal, whether there is pneumothorax or no pneumothorax, intracranial hemorrhage or no intracranial hemorrhage, etc. But this article, which I'm going to discuss, actually breaks all these barriers. So this used deep learning algorithms to detect critical findings in Head CTs. And I do have a disclosure to make. This is an India-based startup, and I actually know a few of the people involved in the study. But the Lancet journal editor certainly did not know these people. So let's go and look at the study in detail. It looked at CTs which were done on an emergency basis for trauma or suspected stroke, and it tried to develop and validate a set of deep learning algorithms for automated detection of multiple key findings and not just a binary thing. So it looked to detect intracranial hemorrhage as also subtype it, whether it's intraparenchymal hemorrhage, intraventricular, subdural, extradural, or subarachnoid hemorrhage. Also looked at calvareal fractures, presence or absence of midline shift, and presence or absence of mass effect. How many images or how many CTs were included? So that's, I think, the biggest strength of the study. This was a real large data set. Over 310,000 head CTs were included in the study. After excluding post-operations and kids who were less than 7 years of age, they had a training data set of around 290,000 CTs. The original CT report attached to each of these CTs was used as the gold standard, and they used natural language processing algorithms to train the data on the AI software. So for example, if the original CT report said that there is presence of extradural hemorrhage, then the NLP would extract this information and label the CT as one which is positive for EDH, and that is what the AI software would read. After this training, a validation dataset of over 21,000 scans was used to evaluate the software further. And finally, for external validation, the test dataset was used. And this dataset was actually taken from 6 different centers in the city of New Delhi, the capital of India. And the first set of 214 head CTs was actually consecutive CTs performed in a single month across all these centers. And the second set of 277 HCTs was selected positive scans from these 6 centers from the last 6 years of data that they had. So these test data sort of actually evaluated, and the gold standard was consensus of 3 independent radiologists who read each and every CT. So this was a pretty robust study methodological wise. And what did they finally find? So to just briefly tell you about area under the curve, the basic premise is that the closer the AUC is to 1, the better is the result. The closer it is to 0, the worse is the result. And the AI software actually performed pretty well. So for all the different features, including the different subtypes of IC hemorrhage, the AI software had an AUC of pretty much more than zero point 0.9 apart from mass effect, which was 0.86. And it was even better for the test data set, in which case all the AUCs were greater than zero point 0.9. And these are the graphs which show the same thing. But let's look at actual images. So the AI software is pretty good at detecting something like this big, obvious intraparenchymal hemorrhage, a subdural hemorrhage, as also more subtle subarachnoid hemorrhages and chronic subdural hematomas. But there were some erroneous predictions as well. So for example, this was a false negative in which the AI software failed to detect this subtle intraventricular hemorrhage. Also false positive in this case, in which a chronic left MCA infarct was called a subdural hemorrhage by the AI software. And here's an example of a right parietal bone fracture which was missed. And of course, most radiologists have got this because of the associated soft tissue swelling. But remember, the AI software was not trained to detect soft tissue swellings. But despite these few erroneous predictions, the overall AUC was extremely high. And it's pretty clear that deep learning algorithms can accurately identify urgent head CT abnormalities. And this is probably going to allow automation of the triage process. So immediately after an emergency head CT is performed, the software can actually look at the scan. If it is positive, it can immediately send it to the radiologist for reporting on an urgent basis and thus help improve and hasten patient management. Ideally, a prospective study should be performed to determine the safety and efficacy of such a triage because, as we saw, there are both false positives and false negatives present as well, and to look at the overall impact it has on patient outcomes. But certainly, it is a very promising tool to help us take care of our patients in a faster and better manner. I would like to end with this photo of the beautiful Maldivian sunset. Thank you so much. I hope you enjoyed this video.